Okay, good afternoon, good evening, good morning, good night, depending on when you're watching the video. So in this video, we are going to work through the summary exercise from slide 23 of lecture set number 3. In this exercise, we are going to review the general addition rule, the conditional probability rule, and the concept of independence. And along the way, we will also discuss marginal probabilities and intersections between two events, or the probability of intersection between two events. So this summary exercise is going to cover quite a lot of definitions from lecture set 3. All right, so we have a two-way contingency table shown here. There are two variables in this two-way contingency table, as there are in any two-way contingency table. So we have healthcare plan, of which there are 3 levels: fee for service, PPO, and HMO. And we have company size, of which there are also 3 levels: small, medium, and large. We have defined 2 events, A and B. So the event A is the event that a company is medium-sized. Okay, so we can think of A as corresponding to anything across this row. And event B is that the HMO healthcare plan is selected. So we can think of B as corresponding to anything across this column. Okay, in part A, we're asked, what is the probability of A or B? Okay, so first off, to compute the probability of A or B, we have probability A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So to compute the probability of A or B, which is the union, we need the marginal probability for A, the marginal probability for B, and the intersection of events A and B, or rather the probability of the intersection between A and B. Okay, so to find each of these, we can simply use the two-way contingency table. So all 3 of these probabilities boil down to a fundamental calculation. So all the ways the event can occur divided by the size of the sample space, which in this case is the 833,303. So essentially, we view this problem in the context that imagine you randomly select one person from all 833,303 people in this two-way contingency table. A is asking, what is the probability that they work for a medium-sized company? Okay, so the probability that 1 out of 833,303 people work for a medium-sized company is 22,382 divided by 833,303. Okay. Probability of B, this is asking, what is the probability that person is subscribed to a company with the HMO healthcare plan? Okay, same logic as for the probability of A. So this is going to be 242,105 or 105 divided by 833,303 minus the probability that one person works for a medium-sized company that is also subscribed to the HMO healthcare plan. So this is going to be the intersection between those 2 events, which is 6,938 divided by 833,303. All right, from this point, there's a number of different ways that you can work out the union. So for example, we could reduce everything to be one fraction. So that might look something like this. All right, so that's going to give us 22382 plus 242105 minus 6938. Okay, so that's 257,549 divided by 833,303. Okay, and then that's going to give us 0.309. Now you could also just turn each of those fractions into a decimal and then add and subtract those decimals. That would arrive at the same answer. Okay, so that's the illustration of computing the union. Here we are just applying the general addition rule. The general addition rule is the first rule that I wrote that expresses the union in terms of the marginals. So P of A and P of B are marginal probabilities, and P of A minus B is an intersection, or the probability of the intersection. Okay, part B asks, what is the probability of A given B? All right, so we have the probability of A given B is equal to the probability of A and B divided by the probability of B. So this is going to be 6,938 divided by 833,303 divided by the probability of B, which is 242,105 divided by 833,303. This reduces to 6,938 divided by 242,105. And that gives us 0.029. Okay, so in part B, we're computing a conditional probability. Conditional probabilities are found using the conditional probability formula, which is expressed at the start of the problem here. So we have P of A given B is equal to the intersection divided by the marginal. And then you can see what's happening here is the sample size for the problem is canceling out. So we're left with 6,938 over 2,442,105. And that gives us our answer. And if we look back at the contingency table, you can see what's happening here is that by conditioning on B, what we have done is restricted ourselves to this column. Okay, so everything in here is given B. And then we are simply saying, what is the probability of observing a medium-sized company given I have to belong to an HMO company? So if we were to visualize the sample space as only being the column for the HMO outcome, this is saying, given that you're in the HMO outcome column, so imagine there's only 242,105 people total now in the experiment. What is the probability that that person belongs to a medium-sized company? That's just a fundamental probability, 6,938 divided by 242,105. And that's what conditioning means, or the given symbol represents in the context of a two-way table. Okay. Part C, are A and B independent? Verify in two ways. Okay, so recall, if two events are independent, then one of the three things are true. Then one of these are true. Then one of the, well, actually it's all. then these equalities hold. P of A and B is equal to P of A times P of B. P of A given B is equal to P of A. P of B given A is equal to PB. Okay, so we want to verify or check. We're asking to check if A and B are independent. So what that means is we just need to see if, because we have to do it in two ways, we're going to pick two of the rules given here, and we're just going to see if the left side equals the right side. Okay, so let's start with the first rule because we have all these values. Okay. Instead of saying use here, I'm going to say check. Is this true? Okay, so we know that P of A and B is 6,938 divided by 833,303. This is going to be multiplied by, or is this equal to 22,382 divided by 833,303. And we're going to multiply this by the probability of B, which is 242,105 divided by 833,303. Okay, so P of A and B is 0.008. And then P of A is 0.027. We're going to multiply this by 0.291. All right. 0.027 times 0.291 is equal to 0.08. Oh, look at that. It's pretty damn close. Oh, okay. We're going to need another decimal place, I guess, just to show. They have to be exactly equal, but the rounding here makes it look like it is equal. So this is going to be 0.00833. Okay, and then 0.00833 does not equal 0.00786. So it is pretty close. Okay. So because the left side does not equal the right side, this means that they are not independent. Okay, and then we have to check in two ways. So next we can check, does the probability of A and B equal the probability of A? The probability of A and B from above is 0.029. The probability of A is 0.027. So since these do not equal, these are not independent. Okay, so in this exercise, we have seen an example of computing the union between two events. So part A is asking for the probability of a union, which is given by the general addition rule. In part B, we have computed the conditional probability, which uses the conditional probability rule. A conditional probability is essentially a probability that's been restricted to only one portion of the entire sample space. And then in part C, we're checking for independence. Independence holds if any one of these three equations hold. So P of A and B is equal to the product of the marginals. P of A given B is equal to P of A, or P of B given A is equal to P of B. So I've used the first rule. Left side does not equal the right side here, so they are not independent. And then I've also used P of A given B is equal to P of A for illustrative purposes. And here you can see left side again does not equal right side, so they will not hold. In general, we only need to use one of these equations. If one of them holds, all of them will hold. If one does not hold, then none of them will hold. But we're using two different equations for illustrative purposes here. Okay, as always, if you have any questions, please let me know.